Welcome to Mastering Solutions. In this question, we have to draw a picture of what's going on here, and then they want us to label everything and give numbers for all of it. So let's start by just drawing a line, and they say that there's 750 lines per millimeter. Obviously, we're not going to draw all that, so we'll just say this little line right here, that's where the diffraction grating is for this question. Now, we know that over here, the viewing screen is given, and that is going to be L. So that distance there. Okay, so that's L, and it is equal to 1 meter, they said. So if we draw a diffraction grating, the pattern is going to be, we'll have a central maximum, kind of like that right there. And then next to it, for m equals 1, we'll have a little bit smaller of a maximum, and the same distance away, we'll have a little bit smaller right there, and these two are the same height. So right here, let's label this. This is m equals 0 because it is the central maximum. So that's y is 0 meters because we're at the central maximum. Y is the difference between this out to another bright fringe. And so here, that distance right there, that is going to have an angle right there, and that is theta. So we'll have the same right here, and that is also theta. So those two angles right there, they are the exact same. And then this is m equals 1, also m equals 1, and y, or the difference from here to right there, that is y equals 1, and same distance down here, m equals 1 again. So now we have to figure out what the distances and everything is. So we need to figure out what the theta is and what y equals 1 is. And of course, they want to label stuff. So that's the screen. And then here's the diffraction grating. So the equations that we're going to use is sine of theta is equal to m lambda over d. We'll have m of 1, and they give us the wavelength lambda 670 nanometers. And then d is the grating distance, and that's 750 lines per millimeter. And so let's plug these in here. And we want theta by itself, so if we move sine over, we're going to have theta is equal to the inverse sine of m lambda over d. And before we plug in the numbers here, it can be really confusing with diffraction gratings of what to put in the d exactly. We're going to figure that out is sometimes students will do 750 divided by 1 millimeter. That's incorrect because for every 1 millimeter, there are 750 slits. So we need to take 1 millimeter and divide it by 750. That will give us the correct grating distance for between every slit. And so we'll have theta is equal to the inverse sine of m is 1 times the lambda, which we said is 670 times 10 to the negative 9 meters. That's divided by 1 times 10 to the negative 3. Or 0.001, right? Meters divided by 750 slits, and that will give us our theta. So we have the inverse sine of 1 times 670 times 10 to the negative 9. That's all divided by 0.001 or 1 times 10 to the negative 3. Divided by 750 slits. And we have 0.52, so we'll just keep that at 0.5. And what is that? Remember, your calculator needs to be in radian mode because it's 5.5 or half of a radian for the angle right here. Now let's figure out the y for here. So the delta y is going to be y is equal to L times the tangent of the angle. And we just figured out the angle, of course, is half of a radian. So L is 1. So really it's just the tangent of 0.5. So y is going to be the tangent of 0.5 radians. And so that is 0.55. So that is 0.55 meters. So the y to each of these is 0.55 meters. Y there is 0.55 meters. And the angle, of course, is half of a radian, and we have everything else labeled. So there you go. That is the answer to this question.